We have seen how social media systems can buckle under the pressure of millions of simultaneous updates. How do we build an architecture to absorb that shock? Let's start with a celebrity user making a post. The request hits a load balancer and moves into our API cluster. In a traditional setup, the API would try to update every single follower's feed right away. This creates a massive synchronous bottleneck where the system stalls, waiting for millions of database writes to finish. To solve this, we introduce a message broker as a shock absorber. Instead of doing the work immediately, the API cluster just publishes a message to this queue. Downstream, background processors subscribe to these messages to handle the heavy lifting at their own pace. Our processors have two jobs. First, they persist the post to the primary database. Second, they perform a fan-out, updating individual feed caches for every follower. Now, when a follower logs in, they simply read from their own pre-computed feed. Let's trace a single post from our celebrity. It travels through the load balancer to the API and into the message broker. At this exact microsecond, the user sees a success checkmark on their screen. The system has accepted the post even though no followers have seen it yet. Now the background work begins. The message moves to the processors, which update the database and the cache. This is the power of decoupling. The API no longer cares how long the database takes to write. The real magic happens here in the feed cache. We are not querying the main database when a follower logs in. We have already pre-computed their specific feed. The latency for this read is incredibly low because it is a simple key value lookup. This asynchronous flow allows us to scale efficiently. Because these workers are independent, we can spin up thousands of them to handle a celebrity with millions of followers without slowing down the initial post request. Our architecture is now resilient to traffic spikes. But this is not the only way to move data to text. Different traffic patterns demand different delivery models, and we will explore those trade-offs in the next chapter. Let's compare traditional HTTP with persistent WebSockets to understand how real-time communication actually works. Meet Alice and Bob, two users who want to chat with each other instantly. In older models, clients constantly poll the server for updates, but we want to move toward a push-based model where clients simply listen for new data as it arrives. A load balancer sits in the middle to handle the incoming traffic. Alice and Bob establish their initial connections through this central gateway. Behind the load balancer, we have our application servers, specifically designed to handle WebSocket connections. The load balancer routes each user to a specific node, using sticky sessions to maintain the connection over time. Unlike standard REST requests, these lines become persistent TCP connections that stay open indefinitely, represented here by these glowing lines showing a live stream of data. This creates what we call a sticky session, which is crucial for stateful communication. Because the connection is stateful, the load balancer must remember exactly which node Alice is connected to. If her packets went to node 2, that server wouldn't have her active socket open, and the message would fail. To coordinate across these different servers, we introduce a pub sublayer. But here is the core problem. Alice is on node 1, while Bob is on node 2. How do these isolated servers talk to each other? We connect our servers to the pub subsystem, allowing them to publish and subscribe to specific message topics. This pub sublayer decouples the architecture. Node 1 doesn't need to know Bob's location, it just needs to tell the topic that a message exists. We also add a message store database to ensure our chat history is saved for durability. Node 1 is linked directly to this database to persist every interaction. Let's trace a real-time message where Alice sends a hello to Bob. The packet travels from Alice through the load balancer and arrives at node 1. Node 1 receives the data and begins processing the request. First, node 1 persists the message to the database to ensure it is never lost. Now for the real-time magic. The server publishes that message to the pub subtopic. Inside the pub sublayer, the message is broadcast to all nodes interested in Bob. Node 2, which is subscribed to Bob's topic, receives the message immediately. Node 2 then finds Bob's active socket in its local memory and pushes the message directly to him. Bob receives the message in milliseconds.
By using this persistent loop, we bypass the heavy overhead of establishing new handshakes for every single character typed. Now that we see how the basic path works, let's clear away the details to focus on the next level. This architecture works great for a few users, but it introduces a massive new challenge. How do we scale this environment to handle millions of persistent sticky connections simultaneously? Let's move our core components over and look at the scaling strategies required to handle that kind of massive real-time load. Implementing conflict-free replicated data types, or CRDTs, is often the most resilient choice for building distributed systems. Imagine two users, client A and client B, connected to a central sync engine. Both clients maintain a local first state, allowing them to work independently on their own copy of the data. If we represent a string of text as a list of characters, CRDTs allow us to track every single item across the entire network. Notice how every character is assigned a unique, globally sortable identifier. This metadata is the key to resolving conflicts without needing a central authority to decide who is right. When client A appends an O at the end of the word, it is assigned a specific ID. Simultaneously, client B inserts an exclamation mark in the middle, giving it its own unique identifier. These operations flow to our sync engine as specific mathematical instructions. Because the logic is commutative, the order in which the server receives these packets does not change the final result. Since ID 1.2 is mathematically smaller than 1.5, the system knows exactly where to place each character. The resulting state is deterministic across all nodes regardless of arrival time. After the server replicates these updates, both clients reach the exact same state. This is convergence, the fundamental promise that makes CRDTs so powerful for collaboration. But what happens if the network fails? If client B goes offline, the system does not break. Client B can keep typing, and these changes are held in a local offline buffer. Once the connection is restored, the system flushes those buffered operations to the sync engine. Below the engine, a state store maintains the full causal history of every change ever made. The server does not need to resolve conflicts. It just stores and forwards these immutable operations. Client A then receives the buffered updates, and the two states merge seamlessly. The system recovered without requiring a single manual merge conflict dialog. However, this high resilience is not free. The state store must keep track of every ID and even markers for deleted items known as tombstones. This leads to significant metadata and storage costs that grow over time. As we move forward, we will see how this growing history creates new challenges for our architecture. The real challenge in building real-time systems is moving from a pull-based architecture to a push-based one. Our current setup with a read replica relies on the client asking for data. But to achieve instant updates, we need the database to push changes to us as they happen. One common way to handle this is long polling, where the client constantly asks the database if anything new has arrived. It is a simple strategy to implement, but the client is essentially just knocking on the door over and over again, usually finding nothing. While simple polling creates massive overhead when your user base grows, when hundreds of clients ask for updates simultaneously, the database spends more time answering empty requests than doing real work, leading to high latency and wasted resources. Alternatively, we can use database triggers to push data out immediately. When a change happens, the database fires a trigger that sends a notification to an external webhook service. This offers much lower latency, but it introduces a major performance risk. In this model, the network call becomes part of the database transaction itself. If the webhook is slow or the network hangs, your core database transaction stalls, potentially locking up your entire application and exhausting connections. This brings us to logical decoding, also known as change data capture. Every time Postgres makes a change, it first writes that change to a write-ahead log for recovery purposes. We can tap into this existing stream using a logical decoder. This process is completely asynchronous, which means it has zero impact on the performance of your transactions, while still delivering updates with sub-10 millisecond latency. Let us compare the three options. Polling is easy to set up, but is slow and heavy on resources. Triggers are fast, but pose a significant risk to your primary database stability. Change data capture provides the best of both worlds, with minimal load and extreme speed. Because it balances performance and reliability so well, logical decoding is the gold standard for high-scale real-time engines.
For a truly scalable engine, the choice is clear. We use a dedicated real-time engine that decodes the log and pushes updates to subscribers. Let us look at how this architecture handles a single row change from the database all the way to the end user. First, the change is committed and recorded in the log. Then the engine decodes that specific change and finally pushes it out to all connected subscribers instantly.